MS Ramaya University of Applied Sciences.
Hi students, let us discuss the design and construction of asynchronous counters. Aim of the experiment is to design and construct an asynchronous counter. A counter is a very simple device which counts from 0 to n. Some counters allow to hold the value or to increment one at a time. Two types of counters exist, synchronous and asynchronous. An asynchronous counter is called so because not all the flip-flops are hooked to the same clock. A 3-bit asynchronous down counter, truth table and timing diagram are as shown. The 3-bit asynchronous down counter logic diagram is as shown. The 3-bit asynchronous up counter logic diagram is as shown in figure. The apparatus required for this experiment are trainer kit, connecting probes, JK flip-flops. Procedure for verification of asynchronous counters. The truth table and a design of asynchronous counters are given. Realize this circuit on your board by using logic circuit. Connect inputs and outputs correspondingly. Connect the functions outputs to LEDs. Verify input bar output relation, that is truth table of counters. Conclusion. The functionalities of asynchronous up and down counters have been verified experimentally.
Hello students, name of the experiment is Design and Construct Asynchronous Counter. Aim of the experiment is to design and construct 3-bit asynchronous up counter and down counter. So now the apparatus required for this experiment are digital IC trainer kit. So this is the digital IC trainer kit which we are using to perform the experiment. So now here you can see at the top there are 10 red color knobs and 10 black color knobs. This 10 red color knobs represents the output, and the output can be seen through this LED bulbs, and the 10 black color knobs represents for the input, and the input can be seen through the LEDs here. And this inputs can be varied by varying the toggle switch which is at the bottom of the each input knob. So this is logic high, this is logic low, and here you can see there are 4 IC bases where you can place different ICs. Now each IC base consists of the IC slot. There are 16 slots are there here. So to place IC which consists of 16 pins. So now here in this experiment we are using 7476 IC which consists of 16 pins. So therefore all the slots will be occupied by the IC, and these knobs which are there at the IC base represents the each slot of the IC base, and there is also VCC and ground which is there to power up the IC there and the IC base. And here there are 5 clock signals of various frequencies: 1 Hz, 10 Hz, 100 Hz, 1 kilohertz and 10 kilohertz. And also you have a mono pulsar here. This is for positive edge trigger, this is for negative edge trigger. So here we can use either mono pulsar or standard clock signals for this experiment. And here you can see there is a continuity tester to check the patch cord continuity. So by placing the patch cord here, if you get a beep, so that means the patch cord is working fine. So in that way we can check the patch cord's continuity here. So this is about the digital IC trainer kit. 7476 ICs. These are the two 7476 ICs which we are using to perform asynchronous up counter and down counter. Both ICs are 16 pin ICs and patch cords which we are using to connect the circuit. Now let us connect the logic circuit based on the given logic diagram. Before connecting the logic diagram, let us check the continuity of the patch cords by placing each patch cord into the continuity tester. So take the patch cord, So turn on the power supply of the digital IC trainer kit. The LED bulb is on, the power supply is on now. So now we have to place each patch cord into the continuity tester. There is a beep noise and LED is on, that means this patch cord is working. So this test is performed for all the remaining patch cord in a similar way. Now let us place the IC into the IC base. Make sure while you are placing the IC into the IC base, the notch at the IC should be always at the upward direction. Here is the notch, so therefore I am placing it in a upward direction. So place it into the IC base and close the lever. Make sure the IC is not coming out. Similarly, the another IC I am placing into the second IC base. It's a 16 pin IC. After placing it, close the lever. Let us connect the logic diagram. So according to the given logic diagram, pin number 1 of 7476 IC is connected to the clock pulse. I am selecting a mono pulsar, so I have connected here. Then pin number 4 and pin number 16 are shorted, and from that it is connected to VCC. So VCC is here. Then pin number 15 is connected to pin number 6, and pin number 9 and 12 are shorted, and from that you have to connect to VCC, that is here. Then pin number 11 is connected to pin number 1 of the second IC base, that is 7476 IC, and pin number 4 and 16 of second IC base is shorted, and from that it is connected to VCC here. Next, pin number 15 is output QC. I am connecting here output QC, and pin number 2 and pin number 2 of both IC bases are shorted, and that is also shorted with pin number 7 of the first IC base. From that it is connected to VCC again. Pin number 3 of the first IC base and pin number 3 of the second IC base are shorted. From that, pin number 8 of first IC base is shorted. So from there it is going to VCC. So I will connect here. So pin number 13 is ground for each IC base. According to the pin diagram, it is ground. Pin number 13 is ground. Now let us connect the outputs. We have connected one output QC, and QB I will connect, that is pin number 11 of first IC base. This is QB, and the last output QA, that is pin number 15. It is from here. I am connecting pin number 15, and it is output QA. So now this completes the logic circuit. Now let us verify the truth table according to the given truth table. Before that, we have to turn on the power supply to the digital IC trainer kit. The power is on. So now we can see there are 3 outputs, QC, QB and QA. So these are the outputs are connected. Here this circuit is for up counter. So now first I will make 0. So now here you can see I have connected a clock pulse. For every clock pulse it should increase in the count. So now right now the output is 0 0 0, that represents 0. Then I will press the clock pulse, or I will give the clock input. So you can see the output has been increased by one number. The output is 1, that is 0 0 1. For the second clock pulse it should increase by one more number. So now it has become 0 1 0, that represents 2. Similarly for one more clock pulse it will become 3, that is 0 1 1. Next one more clock pulse it will become 4, that means it is increasing. So it is now 1 0 0. For the next clock pulse it is 1 0 1, represents 5. So for the next clock pulse it will become 1 1 0, represents 6, and one more clock pulse I will give, it will reach to the maximum value, that is 1 1 1 7. So again if I press the clock pulse it will come back to the 0 position. So again it will repeat. So this completes 3-bit asynchronous up counter. So we have completed with 3-bit asynchronous up counter. So now let us construct a 3-bit asynchronous down counter as per the given logic diagram. So now the connections are similar to the 3-bit asynchronous up counter, only 2 pins has to be changed. Now let us connect the 3-bit asynchronous down counter. The connections for the down counter is similar to the up counter, only 2 pins has to be interchanged. So that is pin number 15 is connected to pin number 14, and pin number 1 is connected to pin number 10. So remaining outputs everything will be same, only I have changed pin number 1 to pin number 10 and pin number 6 to pin number 14. So this completes the construction of the down counter. Now let us verify the truth table according to the given truth table. So for that we have to turn on the power supply to the digital IC trainer kit. The power is on now, and these are the 3 outputs. It is a down counter, QC, QB and QB. So for every clock pulse the count has to be decreased by one number. Now you can see the output is 1 1 1, that means it is 7. For the next clock pulse it should become 6. So let us check it. So I'm giving the clock pulse. You can see the output has been decreased by one number from 7 to 6, that is 1 1 0. For the next clock pulse it should decrease by one number again. So it has decreased to another one number. So for the next clock pulse again it has become 4. Next clock pulse it will become 3. So next clock pulse 2. Next clock pulse 1, and another clock pulse it will become completely 0, and the cycle repeats for the next clock pulse. So again it has reached 7, 6, 5, 4, 3, 2, 1, 0. So now this completes the 3-bit asynchronous down counter experiment.
At MSR UAS, we spark your imagination unlike any other.